So now let's specifically take waves and look at sound waves. Sound wave is a type of longitudinal wave. So that means the motion of particles and motion of the wave are parallel to each other. A sound wave specifically looks something like this. So for example, a sound created by a string vibrating back and forth. So here's our string. It's going to vibrate all the way to this purple dotted line and back to this purple one and back and forth and back and forth. As it comes out to this side of the purple line, what we're creating was we're pushing all of that air. Since the air is going to resist that motion, sort of all the air particles are going to compress, and we get an area of compression. On the opposite side, because it's sort of pulling air away this way, we get this area of very low pressure called rarefaction. So this area of compression is kind of like the peak of our wave. Rarefaction is sort of the top of our wave. So if we were to maybe make a graph of this wave moving through time, instead of maybe some normal thing like distance or something here, we might put pressure. And so it alternates from areas of high pressure, low pressure, high pressure, low pressure, in that same sort of wave pattern that we're used to. The speed of sound is just what it is for all our other waves, and that the velocity of the wave is equal to our frequency times the wavelength of the wave. So that doesn't change at all, follows the same behavior as any other wave. What does change, and what's interesting to look at, especially with sound, is how velocity varies from substance to substance. Because sound involves the movement of particles back and forth, the way those particles are put together in whatever particular medium sound is traveling through actually makes a difference in how fast that sound can travel. For example, in air, where particles are fairly spread out, we have a velocity of 331 meters per second at sort of room temperature air, which is fairly fast, but not compared to, say, something like steel, where particles are already very close, very compact together in that solid, and we have a velocity of 5,960 meters per second. So sound travels a lot faster through steel than it does through air. So what the medium is made of and how those particles are arranged in that particular medium actually makes a fairly big difference. Another interesting thing to look at, especially with air and with gases in general, is how temperature affects the speed of sound. Right? Low temperature would mean denser air, so particles closer together. Higher temperature means things are more spread out, moving around faster, and so it's maybe harder to make that wave move. So there is a temperature dependence, and we have an equation to calculate that. We take our velocity of sound in air as our usual 331 meters per second, like we said above, but then we can change it based on the temperature by taking our temperature in Kelvin divided by 273 Kelvin. So this temperature here, make sure you note, is in Kelvin, not in Celsius or Fahrenheit or anything like that, but in Kelvin. Divide that by 273 and you get 331. So this is actually, I was mistaken before, this is the velocity of air at 0 degrees Celsius, or freezing point, because that would be 273 Kelvin, so divide by 1, square root of 1 is 1, and there we go, 331 meters per second. But we could find it theoretically for any temperature. In general, sound intensity is kind of just like any intensity, is power per unit area. So power might be, how many watts is the speaker that it's coming out of. Area is sort of the area of the sphere that would be created at that distance. So usually when you're dealing with this, it's power over 4 pi r squared for surface area of a sphere. And this r here is sort of the distance you are away from the speaker. So let's say maybe 400 watt speakers. At 1 meter, you put 401 there. However, measuring intensity this way doesn't do us a lot of good because it actually doesn't match the response of our ears and how we perceive intensity. A better way to do that is through decibels. Decibels, the equation to calculate how many decibels something is negative 10 log intensity over what we call intensity naught. It's a logarithmic scale. That's actually how your ears respond to sound. This is the intensity of the sound you're listening to, and this I naught is something that we call the threshold of hearing. It's sort of the lowest intensity sound that you can hear for most frequencies. And it's 1.0 times 10 to the negative 12 watts per square meter. So anytime you see that intensity naught, you're going to plug that value in there. And that's actually a better match for how our ears respond. So let's take a look sort of at how this logarithmic scale works, because that's kind of an important thing. So a logarithmic scale is going to look something along the lines of this. Actually, let's maybe make that a little bit bigger so that we can see it. Where sound intensity, this is in decibels, 0, 10, 20, 30, 40. So we're going up by 10 decibels every time. But you'll notice every time we go up by 10 decibels, we go up by a factor of 10 in intensity. So a change in 10 decibels is a 10 times change in intensity. And that's how a logarithmic scale works. So it's slightly different than what we're used to. However, there's a couple cool little tricks that we can use to sort of help us out. When we look at this, kind of easy things to remember is if you double your intensity, so if your second intensity is twice as much as your first, that's a 3 decibel difference. A 5 times difference, so 5 times as much intensity is a 7 decibel difference. And like we said before, a 10 times difference in intensity is 10 more decibels than the sound was previously. So these are kind of just nice little shortcuts that we can use sometimes when thinking about how do two sounds compare to each other. We claim in the previous part that a difference in 3 decibels means a sound is twice as intense. Let's actually prove that to ourselves using the equation. So what we know from this problem is that I2 over I1 is equal to 2. Our intensity is twice as much. We also know that our difference in decibels, so decibel 2 of sound 2 minus decibel of sound 1, is 3 decibels. Okay, and so that's kind of what we have to work with. And we also need to sort of remember a little bit about how logarithms work. Right, remember our equation is decibel equals 10 log intensity over intensity naught. So we could set that up for intensity number 2 and intensity number 1 and start working from there. But it helps if we think about logarithms first. If I take my 2 decibel levels and subtract them, so let's say that's decibel level 2, so that'd be intensity 2. So decibel 2 minus decibel 1, what we have written up here, would look something like this. We'd have 10 log of intensity 2 over intensity naught minus 10 log intensity 1 over intensity naught. Well, if we follow the rules of our logarithms, you can actually, when you're subtracting logarithms, you can make them into a fraction and say 10 log of intensity 2 over I naught divided by intensity 1 over I naught, and that's kind of a rule for how logarithms work from math. Our intensity naughts cancel out, so our sort of change in decibels, if you will, is equal to 10 log I2 over I1. Well, that would be 10 log 2, which is equal to 3. If we were getting a little more specific, if we were really carrying this out, it'd actually be 3.01 decibels, but that's pretty darn close to this. And for all practical purposes, for anything we're doing, this assumption is close enough. So twice as much intensity means an increase in 3 decibels, and that's kind of a good one to try and remember.